So we know that if we have a free body diagram and we have a bunch of x and y forces, we can use that in Newton's second law to find the motion, the acceleration of the object. Okay, so if we have a free body diagram and we pick positive directions for the x and the y, in other words, if we pick a frame of reference, FOR, frame of reference, and all I mean for frame of reference in this case is picking a positive directions, two positive directions currently, okay? Then I can use two Newton's second law equations and I can solve relating motion to forces. Very commonly what happens is you end up having some, one of these will have equilibrium. So one of them, you have the sum of forces in the x direction equals ma in the x direction, and the sum of forces in the y direction equals ma in the y direction. And very frequently, in fact usually, you end up, one of these is in equilibrium. Either I'm dragging an object across the ground and it's not accelerating up or down, it's not plunging through the Earth's surface. So so acceleration in the y direction is 0. So it's in equilibrium. The sum of forces equals 0, so the total up equals the total down. Or if you're in an elevator or something like that, then you have some y acceleration, but generally you don't have an x acceleration. So usually one of these equations is pretty easy. And in fact, in that case, you're using the y acceleration to find an unknown force, frequently normal force, something like that. Okay, so these go in both directions. Alternatively, if there is an acceleration but we don't know it, we could use all the known forces to find the acceleration. And that's what we're going to be doing today. We're going to be talking about that. We've definitely done a lot of problems like this, right? But the next step we have is this concept of angled forces. And, you know, it's not a real big worry, but if one of these, instead of like that, is like this, well, that doesn't fit in here. It doesn't fit in here. What we have to do is break this into components. We need to figure out, we're reducing it to a previously solved type of problem where we have everything orthogonal, everything perpendicular. So what we do is we take that and we, here are the forces that were there already. Here are all the other forces. They don't change. But we put this into that frame of reference. So what we do is we put these new forces. Let's call that F. This is F cosine of theta. And this is F sine of theta if the theta is from the x direction. And I keep seeing x and y instead of horizontal and vertical because we could be looking down on an object. I could be looking down on this and things are pulling this way. And I don't care about this dimension, but I care about these two dimensions. An example might be, oh boy, it's hard to come up with one. If you've got people doing, you're at lunch and you've got a food tray and somebody's pulling it this way and this way and this way and this way, so it's a two-dimensional situation. If we look down on it, okay, then we don't see mg and we don't see the normal force. That wouldn't show up in here at all if you're looking down on this. So then it is just x and y. It's not horizontal and vertical. It might be east, west, north, south. It might be something that has absolutely nothing to do with any of the standard directions we're used to. But if we can make them perpendicular, picking two perpendicular, and I sometimes say orthogonal, which is a little stronger than perpendicular. It means perpendicular and this doesn't affect this. We can solve these with two Newton's second law equations. So this is the thing that I use all the time. Free body diagram, frame of reference, break it into an x and a y and get any angled vectors and break them into those two directions. Then draw your two Newton's second law equations. And it ends up not being that bad. This is something you've done before with angled vectors, right? You did these things with orthogonal vectors already. So it's really just combining the two things. It's a very straightforward approach that allows you to solve significantly more complex problems because not everything is always perpendicular. Okay, I'm going to push a lawnmower. In the lawnmower, I am pushing, let me just draw a little picture here. Here's the lawnmower, here's me, and I'm pushing on the lawnmower. I'm pushing in that direction on the lawnmower. The lawnmower has a mass of, I'm just going to say 10 kilograms. Okay. And friction, I push with a force of 100 newtons. That's how hard I'm pushing at an angle of 30 degrees. The force of friction is 60 newtons, force of friction. And I want to find out the acceleration. So once again, the approach, free body diagram, that's not a free body diagram there, frame of reference, and what I mean by that is pick positive directions for x and y, and make sure all the angled vectors are in those two directions, and then two Newton's second law equations. Free body diagram, frame of reference, two Newton's second law equations. So let's do that. First of all, the free body diagram. And as always, don't take the free body diagram lightly. That's where a lot of people go wrong. Then all this stuff is garbage. Okay, so free body diagram. Let me do it as a box. I don't know what the, okay. Field force, mg. Oh, I've got the mass. 10 times 10 is 100 newtons straight towards the center of the earth. I go around this thing, everything else is a contact force. There's contact. It's a surface. Surfaces normally have normal force. I shouldn't say that. Usually have normal force perpendicular to the surface. That happens to be straight up. Doesn't end up being 100. Be really, really careful with this. Okay, we have to solve for that. And friction, opposite the direction of motion. It's going along this way, friction is pushing back in the other direction. That is a given. Force of friction is 60 newtons. I keep going around there. Oh, there's contact. And that's me pushing in this direction, also with 100 newtons. Okay? And that's the applied force, so I'm not going to write that in. Oh my word, my pen keeps falling apart on me. So we've got four forces. Now notice, I don't know what the normal force is because some of me pushing is pushing down. It makes the ground push back harder. So the normal force is going to be greater than 100. I don't know what that is right now. Hey, how would I solve this? Well, I got the free body diagram, frame of reference. I'm going to pick this direction positive. I'm going to pick this direction positive. I'm going to have to break this down into components in those directions. Okay? Now, what I want you to do is redraw. This is the free body diagram. I want you to make a diagram that has all the forces the way they were if you don't need to change them. Okay, that doesn't need to be changed. That's in this frame of reference. That doesn't need to be changed. Normal force doesn't need to be changed. This does need to be changed. And I'm going to replace that with two vectors. How much of that goes in this direction? That's 100. And I said 30 degrees, so I'm pushing down at 30 degrees. This is going to be 100 cosine of 30. And this down, it's down and to the right, so 100 sine of 30. This is 86.6 newtons. This is 50 newtons. Okay. If the handle was like this and I was pushing down at a bigger angle, this would be a bigger number and this would be a little smaller. If I push straight down, this would be 100. This would be 0. Okay? So these two things replace that. If you push at 30 degrees with a force of 100 newtons, it's equivalent to if you have a friend go, I'm going to push this way at 86.6, and another friend says, I'm going to push down with 50. It'll have the exact same impact on the lawnmower. So really important to understand that. This gets removed and replaced with these two. Free body diagram, yes. Frame of reference, pick your positive directions, and then make sure everything is orthogonal. Everything is perpendicular. Replace all angled vectors with perpendicular vectors. Then 2 Newton's second law equations, and that's not too bad. First one I'm going to do is the y, okay? Because you are going to want to find normal force. Think of this. If we ever had mu given, the coefficient of friction, we wouldn't know this number unless we knew normal force. So you always want to find all these forces. So let me do sum of forces in the y direction. Okay, let me just write it as y equals ma. And once again, the lawnmower, I'm hoping your lawnmowers at home don't mysteriously fly off the ground or plunge down through the ground. So this acceleration is going to be 0. It's in equilibrium vertically. Normal force is in the positive direction, positive, minus 100, minus 50, those are pushing in the negative direction, equals 0. Normal force equals 150 newtons. Since I'm kind of pushing down on that lawnmower, the lawnmower's weight and the force that I'm giving it vertically, that part, are both pushing down. The ground pushes back. It gets compressed. It presses back with more force. Okay? So that's now 150. Again, if I gave you mu of 0.3, let's say, you could just use mu times the normal force and find the kinetic force of friction. But I gave you the force of friction. So let's look at x. Okay, sum of forces equals ma. Trying to find that acceleration. What's it accelerating at? Well, we got 86.6 in the positive direction. That's the positive direction. Minus 60 equals the mass, 10, times a. 26.6 equals 10a. Acceleration is 26.6 divided by 10, which is 2.66 meters per second squared. It's positive, therefore it's going to accelerate in that direction. Okay? So notice what I did. First thing, free body diagram. Free body diagram. Second thing, pick positive directions for your 2 perpendicular axes, and then break any angled vectors down and replace the angled vector with the 2 components. This and this together, if you did Pythagorean theorem, would equal this. Okay? Then 2 Newton's second law equations. Free body diagram, frame of reference, 2 Newton's second law equations. We're going to do this over and over and over. So I did y first. I didn't even need to do y. I wasn't asked for normal force. I was asked for the acceleration. But I happen to know that the acceleration vertically is 0, so it made it easy to solve for normal force. I could just look at that and say if it's not accelerating up or down, it's in equilibrium, so this plus this has to equal that. But I did it formally. Okay. Then in the x direction, sum of forces equals ma, and when I solve, I get the horizontal acceleration. This is the way it's always going to go. Free body diagram, frame of reference, 2 Newton's second law equations. If I gave you the acceleration, you could use that in here to solve for an unknown force in this direction. But all of this, if you can remember this, free body diagram, frame of reference, 2 Newton's second law equations, you're going to be in great shape. The only trick that we've done that we haven't done before, we did free body diagrams before. We did frame of reference picking positive directions before. The only thing we didn't do is we didn't have angled vectors. So the big change that we got now is we got to take that angled vector and replace it with the components. Then it's exactly the same as we've been doing all the other